let's get started. And I will award 2 t-shirts for good questions, so be prepared. So, hi everyone, thank you for coming. I will be talking about large-scale fuzzing. Do it efficiently. I work for Google Chrome security team, and I'm a part of Bug Bounty and Balalaika CTF team, just like the majority of other young members of this conference. This is my agenda. I'll be talking about Google Chrome because this one I work with, but the same fuzzing techniques should apply to a number of other products. Next, we'll talk about libfuzzer. I'll give you a bit of stats on bugs. I will also advertise our vulnerability reward program and how you can take part in this program with ClusterFuzz. Experienced people are telling me I have way too many slides. Okay, definition of fuzzing. It's a software testing technique that involves passing invalid, random, or unexpected inputs. Well, I say random, but it better not be random, because the idea for us is to track the behavior of a program and discover anomalies, be it security flaws or other logical or functional bugs. The big threes in fuzzing include the fuzzers themselves. So these are the things that help you find new bugs and new vulnerabilities. Next you have memory tools. And finally, scale. Because there is a simple correlation in the world of fuzzing. The more you do and the faster you do it, the better will be the results. So ClusterFuzz is an infrastructure that Chrome is essentially fuzzed within Google. Shown in blue are external reports for vulnerabilities, and shown in red are internal vulnerability reports. You see this huge spike around 2012, and that was the time when ClusterFuzz was launched. And there was another big spike in 2014. That was the time when we switched on Memory Sanitizer, and it helped us discover a huge number of bugs we couldn't see before. So ClusterFuzz itself runs on App Engine and Compute Engine, and some of the devices are running from labs. I'm not sure you want all the details, but the big idea is that there is web interface, which is pretty heavy, because they suck information, draw information from a number of tables. They collect stats from a number of different fuzzers. And we also have a collection of bots that share data storage. They also have the local small storages. But most importantly, each of them runs a list of tasks. So each bot at any given point in time is either fuzzing or minimizing the results of successful fuzzes. So, for example, it can do sort of historical analysis, trying to track who introduced this or that bug, in what particular fork of the code. The objective for creating such a huge infrastructure was as follows. Actually, I've been part of Google Chrome security for over a year, for a little over a year, so that was before my time. But this is how the idea is: to automate crash detection, analysis, and management, to make sure that every crash we're going to report could be reproduced, and ideally We want to minimize it because debugging 100 blob of data is very different from debugging a 100K blob of data, and we want to do real-time regression if we see a recurrence of the same errors. Well, as usually, the programmers, software developers, want to press a single button and see how the whole system works without them. So this is how ClusterFuzz lifecycle works. We first find a fuzz, then we make sure it's actually reproducible, because some crashes are contextual. For example, you can have a memory leak for some time and then you have a crash. And they are not as dangerous as one-shot fuzzers. So then we do analysis, we do deduplication of test cases, because when you have 12,000 cores, very often you will find the same stuff, and you can't really sort them out manually, so you need to distinguish between them to identify the unique ones. After they've been fixed by the developers, make sure that all the fixes have been replicated, so to speak, and then you just manage the versions. So fuzzers can be broken down into 3 types. The first one is generation-based fuzzers. So they simply generate pretty much a random input. Well, better fuzzers will generate inputs that are actually legible, sensible. Well, that would be an example we discovered in WebKit quite some time ago. So the fuzzer used such tokens in JavaScript, so he would permutate them until it found bugs. Another one is actually mutation-based fuzzers. So these guys do not generate data from scratch. Instead, they use a library of valid operands, valid files. So they will read these files and will do simple or not so simple permutations on them. They can swap neighboring bits, for example, or they can do something that's more sophisticated, but still they will take into account the syntax. For some reason, we also have evolutionary fuzzers, but they're called evolutionary because they include several different types of fuzzers. So they do both generation and permutation, and you can also have a library of formats that you want to draw from. And ideally, you would also get some feedback from your target, such as code coverage feedback, and that way you will know whether your recent input actually made sense or not. Well, this is a heap buffer overflow that we found with libfuzzer. For optimization, we need the right infrastructure, and you need to make sure you're always using the latest builds, and all the parameters must be properly sort of tested, because otherwise there will be such a huge fluctuations across the bots and across the fuzzers that you won't have any reproducibility. Duplication of test cases, I'll cover that quickly. So the plan is that we'll use 3 factors from every crash. That is crash type, 3 top frames from crash state, include namespaces but no line numbers. Because line numbers are not a valid indicator, really, they change way too much. There is also an automatic flag that Chrome sort of automatically sets up, showing whether it's a dangerous crash or not, and is based on our attacker model. Now we also track code coverage, and this is actually one of the more objective factors that can tell you whether your fuzzing effort is effective or not. Because that way you will pretty much know which parts of the code you are addressing. And the higher your coverage, the richer your input data will be. I've mentioned that we're already operating 12,000 cores. About half of them are Linux, because things run so much faster and easier on Linux. Linux has always been among the leaders for tasks like this, followed by Android. We also have Windows, both virtual and physical ones, 20 Macs, and iOS is work in progress. Our second objective was to have fully reproducible minimized tests. It's important to maintain the same board configurations. Minimization is based on delta debugging. Nothing new about it, but I have a whole slide on it. Next one. Some fuzzers and some data types, will require their own custom-made minimizers. So the block of data that I want to minimize, we broke down into elements, tokens essentially. Then we generate hypotheses like this. For example, we need half of these tokens for the crash, but not the other one. Which means we do a sort of a binary search, but we do it with the inputs, not with the line. These are the settings for memory tools. So you see here stack trace for red zone of 128. So in one case we thought it was a use after free on the heap, and in the other case was a buffer overflow. Well, since address sanitizer changes the location of individual elements by including red zones and other spatial areas, so to speak, it can have an impact. So it's a bug that needs attention. Next one is regression, checking, and fixing. Well, it certainly pays off to use the latest builds before they've been hacked. Gotta account for bad builds. Because we sort of assume we will find a recently added bug. So look behind window is an important parameter, because if it turns out that this is not a recent addition to the code, then we need to do binary search in order to find a particular commit that edits the bug we are currently seeing. And find bit is a very useful function to find culprit changes. Well, in our browser we have 10 million lines of code, so it could be very difficult to identify the owner, so to speak. And who should we assign this bug to? Now, find it starts with parsing the stack trace. It will extract the numbers. It will try to identify the components that individual teams work on. After it has parsed the stack trace, it will look in the change log or commit log. So it will look at the particular changes that essentially led to the crash. You end up with a short list of suspects. And then if we're able to prove that after a particular commit we actually started having crash, it is shown as the culprit. If none can be found like this, then it will generate a git blame. So that way we'll essentially say, I don't know who the culprit is, but these are all the people who contributed. Now this is an already fixed test case report. And usually it says fixed no until it has been fixed, obviously. But the rest is the same. Crash type, stack trace, bug in the bug tracker, linked. So the person looking at all the crash information should be able to see it. Then you press the button called File the bug. Now you will see the potential culprit. We'll assign the bug to him. And when a bug has been taken care of, Cluster Fuzz will take care of it and will notify the engineers that bugs have been fixed in a range of versions, because so far been able to sort of fire the bug again or crash the system. So we have this bot that actually runs through the code, sets the right flags. Well, some people take their time to fix the bugs, to patch the bugs. And we have this software pretty much incentivizing the engineers to fix the bugs. Okay, these are memory debugging tools. These are different sanitizers we're using, such as memory sanitizer, address, undefined behavior, threat, leak sanitizer, control flow integrity, on a relatively small number of bots, Dr. Fuzz and Dr. Memory. By the way, ASAN is in very good shape. Well, they don't say they're ready for Windows production, but in fact they are. This is a brief description of some of the best tools in this category. The address sanitizer will detect user after free, buffer overflow, container overflows. So in fact, all the issues you might have with addressing in memory is very good. Thread sanitizer could be very good for detecting data races. It's pretty heavy, it doesn't generate a lot of bugs, but it does what it's expected to. Memory sanitizer only detects uninitialized memory reads, and sometimes it's very useful to run these reports because they can give you some sort of transparency into use after freeze. And UB-Sun detects like 20 classes of bugs. Like integer overflow, shift, heap hierarchy, and so on. And it only consumes 10 to 50% of CPU and doesn't require much in terms of memory. I know very little about this Windows stuff. Well, we support them, which means they must work, but I prefer to work on Linux, so I can't tell you much about this. Container overflow now. So you identify a vector, then you do pushback 3 times. Then you will discount, for example, the vector has capacity of, say, 4, which is the subsize of the buffer in the internal implementation of the buffer. But it only has 3 as the size method. And then we start addressing it using the pointer. So we will be addressing element 4, which in the identified buffer, which has a capacity of at least 4, sort of shouldn't be there. So it's sort of more complicated than heap buffer overflow, and it's good that ASUN finds them and reports on them as container overflows. leap fuzzer now. And this is a tool for creating new fuzzers, not a debugging tool. What's good about it? Let's first explain the problems of regular browser fuzzers. Well, this will be generators of HTML or CSS or whatever is displayed in the browser. They have several issues. First, they are targeting a huge amount of code, the whole browser, if you like. Because you can find pretty much anything in a file you open with your browser, so fuzzing individual smaller elements of the code could be pretty difficult. They are not as fast because you gotta start the whole browser. However, these fuzzers are quite good because they can help you identify a number of bugs in the precision engine for HTML tags and what have you. But it would be great to have more granular fuzzing, faster one, with format decoding. We want it to be smarter and easier. So Leap Fuzzer serves most of these purposes. So it works in process, in memory. It won't have to start our target application. So it won't load or switch off the application that is fuzzing. It's actually very efficient and convenient.
Я раньше называл это тоже липфазером, как бы липфазер инструмент и липфазер это фазер, мы объясним с помощью липфазера.
So leap fuzzer is a tool, and I used to call fuzzers produced with leap fuzzer leap fuzzers as well, but that created confusion, so we're calling them target functions now. You can actually produce hundreds of these target functions, and you can check them with a unit test pretty much automatically. And Leap Fuzzer is supported by Googlers, and these are the people who have developed address sanitizer. And I think they presented at 0 nights, which is good for us. How would you come up with the Leap Fuzzer? Now the most important thing is shown here. In order to produce a target function, you gotta identify just a single function. Now this is the function that will be accepting data and reading for their size. So this is the data that the fuzzer will then feed to whatever application. Now we will feed this data to regex open. It actually works. And this is a real example. So that fuzzer found a bug like this. So you found a call on a kind of undocumented function in a third-party library. Well, you can still improve Leap Fuzzer. You can, for example, build better dictionaries for them. A dictionary is a file that contains lists of strings or bytes that will be important for the target. For example, if you're fuzzing HTML, it will contain HTML language, or it can contain JavaScript or PNG if this is what you are fuzzing. So Leap Fuzzer will use these dictionary elements to generate new tools. So we don't even have to explain the full PNG format. Seed corpus. Now corpus is a selection of initial files the fuzzer will work with. So these are the ones that this will read, mutate, and generate. It is very important for the more complicated formats because, for example, creating such a corpus for PDF could be difficult from scratch. But if you sort of feed several PDF files to it, you will be able to reconstruct the basic building blocks from it. You can also produce your custom mutators for the target function. Well, LeafFuzzer has 11 or 12 inbuilt mutators, but they are pretty straightforward. They swap bytes, bits, they introduce or remove numbers, which is not bad, but for the more sophisticated targets, it makes sense to develop your own ones. For protobuf, for example, we do have a custom mutator. So they collect data, they parse data for protobuf.
И, конечно, надо, как всегда, трекать coverage, чтобы понимать,
And we certainly need to track
дальше
coverage
или нет. Ну,
in order to decide whether we move on or not.
И
Again, LeafFuzzer does it automatically. What's funny is that it will check the new inputs in LeafFuzzer. So if coverage doesn't increase thanks to the new input, it sort of discards it. If it increases, which means you've penetrated, you've looked into a new part of the code, then it will be actually saved. You'll see, for example, here that coverage went up by over 25% after we added uregex open. We found 5 new security bugs after we added a dictionary for libxml fuzzer. And PNG fuzzer helps us significantly increase the coverage.
Я тут недавно видел в Твиттере Ник писал, что значит 11 дней фазер SQLite,
Well, you see what Brian said.
Люди там его стали спрашивать,
People started fuzzing him. How come?
SQLite популярная библиотека.
SQLite is, after all, a popular dictionary.
Да, он не использовал слова.
Didn't you use a dictionary? And he says, well, I didn't use a dictionary.
Подсказывает, что четко без словаря хватит, он
And when smart people told him
может в этом случае.
he should have used a dictionary, he said, dictionary wouldn't have been useful. Well, everybody has a right to entertain stupid ideas, but we were able to find 5 vulnerabilities after we added a dictionary. 3 of them include buffer overflows, and one was timeout, another was uninitialized value. Which means that dictionaries are important and you shouldn't underestimate them. LeafFuzzer is integrated with ClusterFuzz, and we use ASAN, AMSAN, and UBSAN builds, and we synchronize the full corpus with all the sort of fuzzer runs. For example, we can be fuzzing XML on 10 bots, and they will be synchronized with the corpus prior to the operation, and they will resync after the end of the fuzzing. So this is how we move with our fuzzing effort. We also added, or rather they also added, scariness to kind of crash scariness ratio or a score to address sanitizer. So you can fuzz it, and you can also sort of set priorities based on the scariness score. We have about 85 target functions. For Chromium, we found 88 bugs, 46 out of them are security ones. Well, I at first was concerned. I thought it was too little, but I was told it was great. They explained that a lot had been fuzzed in the previous 4 years using classical fuzzers. So they say that indeed a LeafFuzzer helps us identify some new things we wouldn't be able to find otherwise. We have about 700 Google Cloud Engine bots running in it. We have, we do like 310 billion test cases per day, which is a lot. But then, given the space we need to search, it's still very little. Corpus synchronization, we do 8,000 of this per day. And we also try to minimize the corpus fuzz, because quite often fuzzers generate sort of the same thing as they work, so we need to do the deduplication. And for a single target, we have pretty good coverage. It's 100% of functions and 89% of the smallest blocks of code. Leaf Fuzzer has been proved to be quite effective outside Chrome as well. So JLeapC, FreeType, and other libraries have been shown to be effectively fuzzed with it. I'm not saying Leaf Fuzzer doesn't have any problems, it does. Well, quite often we find inputs that take quite some time to process or even lead to timeouts, and if such a case goes to the corpus, well, it can easily cost us 5 minutes or even an hour, depending on the timeout we set for it. Another issue is when out-of-memory bugs, well, they're not bugs, they're features in a way. For example, we're fuzzing a particular programming language and we're looking at an array with billions of variables. It simply runs out of memory, right? So the whole thing crashes. Well, sometimes fuzzers just get stuck. You know, they spend hours or days looking in vain for new bugs, and you need to feed new data to it. So you can experiment with a mutator, and like any other fuzzer, it can get stuck at an easy crash. Another real-life example. Since some of the bugs have not been fixed, I'm not showing the name of the library here, and it's a very popular library, so nobody has disclosed it yet. So it's a 10-line fuzzer that was able to find over 10 bugs, including buffer overflow, memory leaks, timeouts, what have you. So you get a target function from leaf fuzzer, you add a dictionary, and off you go. You can actually self-fuzz. I remember there was a mistake that led to crashes of all our fuzzers. Well, if you do fuzzing, you will be the first person to learn that. I think you've previously used other tools such as AFL, so you must be wondering what to use now. AFL is quite popular, so the right answer is that if you combine, that should even work better. So what we are testing now is having a single target function, but replacing engines, so to speak. For example, the target function produced with LibFuzzer can run with AFL. And since their logic for input generation can be different, we can get further. Actually, we tried that already, and these were the results. So when LibFuzzer has been working in vain for several days, we connect AFL, and sometime later AFL will find some interesting inputs and increases coverage, and after that LibFuzzer will also produce something useful. On GitHub you can actually find a proof of concept. It's essentially a converter of inputs. I think of a sync corpus from LibFuzzer to AFL and back. Could be of interest to those who run big projects. Well, we expect all the functions to return zeros. This is bug stats. Now we show them by okay, this is critical bugs shown in purple. Now, most of the security bugs are high severity. Now, according to our guidelines, critical code is the one where you can actually run your process outside the sandbox. So once you've escaped the sandbox, you're considered critical. Well, I think there are about 7,000 bugs shown here, and we had 17 critical ones. So critical are very low. Okay, this distribution by memory tools, you see that ASUN leads the pack for sure. It finds the most popular, such as buffer overflows, point recalls, broken math. And this is stats for vulnerabilities, but the next slide will show all bugs. So you'll see that ASUN has the same share, whatever the type of bugs, while Threat Sanitizer and Leap Sanitizer are much better at finding functional bugs compared to security bugs. So if you're fuzzing for vulnerabilities, I certainly recommend ASUN and MSUN. Everything else will be secondary to them. Okay, our vulnerability reward program. I think you know it. There are lots of bug bounties now. So if you found a bug that you believe is a vulnerability, you submit it to the forum, security sheriff will check it. If it is adequate, then a developer is assigned, and then reward panel will study all the details, such as the criticality of the bug, how difficult it was to fix it, whether the reporter helped us fix the bug, and based on that, they will reward the reporter. Oh, these are the rough estimates. So Sandbox Escape bug can get you about $15,000, and a string of bugs, and this does happen from time to time. You can also sort of get the same amount of money, because if you started with a leak, that will already get you about 4,000. Then sort bypass. You can also get a bonus for a high quality exploit, so that way for a string of bugs you can get like 30,000 USD easily. But that's for a sequence, right? For a string of them. Well, this program has recently been updated. Now the maximum reward has been increased to 100,000, and this is what you can get for a Chromebook or Chromebooks compromising, right? Nobody actually got this reward last year. Nobody was able to do that. That's why the jackpot got bigger. The VRP page is pretty extensive on what is and what isn't bypass. So there are two pretty malicious files that if you manage to download to user without safe browsing and making a scandal out of it, you will get $500 to $1,000. And I saw a case where a guy got $6,000 because he reported similar bugs in different file formats. So high quality report will get you another 1,000 USD. Now the stats are as follows. Last year alone, Google paid out $500,000 for Chrome bugs reports. Since 2010, over 2.5 million have been paid. And median payment has gone up from $2,000 to $3,000. The average payment has gone from $2,700 to $3,600. But median payment is actually more important than average payment. So the best reporters, by the way, take about 70% of the earnings. Maybe they spend enough time looking for the bugs. Our TRP program. When Cluster Fuzz first appeared, people were ecstatic about it.
уважением и страхом, чем, например, сейчас. Я встречал обсуждение, что на самом деле фазер такой угла не очень, и будь народ умнее, получше фазер сделал.
Well, people often say that we could easily produce much better fuzzers than this one. Google could easily come up with something better. So, if you have a good fuzzer, we will set it up in cluster fuzz, we will run it, and if it starts finding bugs, you will get all the bounties you would get had you individually committed these bugs to us, and you would also get $500 from us, because this is a case of high quality report. However, the crashes that it will be able to find should be replicated, so other fuzzers should be able to find it as well within the next 2 days, and you can actually share this price, or even it will be doubled. I mean, if somebody else finds the same bug with a different fuzzer in the same 2 days, you both will get the same price. Target functions are also part of this cluster fuzz TRP program. So you can get in touch with me, or you can get in touch with the Chrome team. This program is designed to be invitation only, but if you've already reported Chrome bugs, you're already considered a trusted researcher. But you know what? If you're here, you're also a trusted researcher. So talk to me, okay? So this program was developed in 2014, and over 120,000 has been paid out over this time, and rewards range from $500 to $4,500. Thank you, I'm done. And I've got 2 t-shirts for the best questions. So be careful. Hi. Artem Himishin from Kaspersky Labs. So you've mentioned cluster fuzz, setting up security flags. I wonder how it does that. Okay, you find a crash, and you might have a pretty high coverage, but how does then coverage go down? Do you reject elements in the cluster through binary search or something? How does cluster fuzz know it's got to stop? The number of iterations it has performed is enough. And by the way, you're inviting everybody. Did you get a cut? Well, formally speaking, I don't get a cut, but that's my job, right? I'm here to find bugs, and if I can delegate it, there's no problem with that. Yes, I do know the logic for security flag installation. So, for example, heap buffer overflow will be considered a security issue. An undefined shift from undefined behavior sanitizer will not be flagged as a security issue. When we read the reports, we just look at the top stack frame, and if we see, for example, that the same counter will be used as a memory offset, that might actually lead to an overflow, so we will manually set up a security flag. I don't really know the answer to your minimization question. I actually spent some time thinking about it yesterday. You certainly get a t-shirt for confusing me with the question. I can get back to you after I've seen the code. Yeah, thank you very much for coming. From what I know, in Chrome, when you download a file, an executable, it will show a warning. And there is a particular resource from which you can start the download and it won't actually give you a warning. Is that a vulnerability? I'm talking about Androids.
Я думаю, вот именно это вряд ли бага, потому что, видимо, какие-то ресурсы
I don't think it's a bug. It could be a trusted resource. No, it isn't.
Ну,
It's a special sort of resource. Well, you can report it
скачать те файлы, которые как раз в сейф-браузинге даны как примеры.
and try downloading the artificial viruses that we have in safe browsing. Well, but there are landing sites that will push exe files. So it's a new resource, a recently registered domain. So it's sort of certainly untrusted resource. Well, it does look like a good vulnerability, but I'm not the one making this decision. They have a reward panel consisting of a team of pretty adequate people, so you'd better submit it to them. I have two questions. Explain this code coverage bit in cluster files. I'm wondering how you measure it. Is that supported in the browser? Or do you measure it in runtime? It's a matter of instrumentation in LLM. So there are Clang, F coverage flags. We use Edge. So you have functions, control blocks. Control block is just a portion of the assembler code. So edges are the smallest building blocks. Do you have an automated manner of getting POCs after doing regressions? That's proof of concept. That's POCs, not exploits. Well, it will be in the report. Once we find a crash and we show it's reproducible, minimization happens. And we'll support it, we'll see the crash again. The moment we stop seeing with this particular POC file, as you call it, we believe the bug has been taken care of. Thank you. Do you fuzz flash, and do you do it at the binary level or not? Well, we do fuzz flash, but we don't do that. Project Zero does it, and I think that Natalia Silvanovich last year got like half of CVEs for that. But I'm not sure whether they work the source code or not. If you send me an email, I'll try to double check that. Okay, imagine you found a particular bug. What kind of diagnostics do you send to the developers? And how much do you make sure that you actually have avoided all similar bugs? How do you foolproof the system, so to speak? No, we don't do it in any automated manner. Well, in some cases we easily know which commits actually added the bug to it, and since the team of engineers and developers is pretty stable, learning curve is pretty steep. Well, sometimes they ask us to fix it, and that's a problem because we don't do that much of code writing. Well, if you have the source code, it shouldn't be a big issue, right? Yeah, I think it's a promising idea because a memory sanitizer will show where the data came from, where it was initialized or freed up. But it doesn't, I mean, the other sanitizers don't do that yet. Do you do regressions on crash reports? Do you include particularly critical reports for regressions? And if you do, then how do you assign priorities? How many reports do you run in a regular regression? Yeah, we do check them, we store them separately. And bots have special jobs for checking that, but we don't have too many of them in cluster files. Well, for some reason we didn't show the numbers there, but say total number of bugs around 7,000 people, and cluster files runs billions of test cases every day. So checking 7,000 test cases in a day is not a problem at all. Do you have any stats on non-reproducible bugs? Yes, we can have a look at stats for irreproducible bugs. Yeah, initially I didn't know how to filter irreproducible bugs out, and I tried to attack them as well. I think we have as many as reproducible ones. Well, I think you can sort of replay it and refine them, right? Well, we asked LeafFuzzer to add a flag that would enable us to run the test input a number of times. And we did have a bug that would sort of pop up once in 10,000 times. So we actually have this rule that it is considered reproducible if it pops up once in, say, several thousand cases. So there was a 2-byte random block summoned in SQLite, and I understand that when these 2 bytes return a particular value, the whole thing crashes. Last question now. Do you do any research into other techniques of dynamic analysis? For example, there has been this research made that show that you do simple execution with particular values. So have you seen any combinations of fuzzing without a dynamic test? That actually sounds like a great idea. It's something I heard from other people and I thought about myself, but I don't think there has been a single project like this. We had a summit for students and postdocs, and there was a guy who told us that he first did a crash and then he did symbol by symbol execution, but he didn't have a code for that, to support that. Which means that everybody is looking into that. That's right. And actually, LeafFuzzer is pretty light, so you should be able to add new stuff to it. It is more promising in this respect. Cool, thank you.